All right. Thanks for listening while we took that short break here at Revolution Radio, freedomslips.com. And now we're going to get back to your host.
Ladies and gentlemen, welcome to another episode of Cosmic Catastrophe on Revolution.radio. I am your host, Diamond, from the Oppenheimer Ranch Project, and joining me is my lovely partner and co-host, Leah Shaper.
Hello.
Welcome to the show. You've got your good mic?
I've got my good mic.
All righty then. We've got a great show. The title of our radio program is Cosmic Catastrophe, and what else would we be discussing except for cosmic catastrophes? In fact, a new paper coming out discusses maybe a mechanism for mass extinctions in the past, and we're talking about big ones, the top 5 big mass extinctions. The article we will discuss is violent supernova triggered at least 2 Earth extinctions, according to a new study. Now, I read the study, and I don't know. There's a lot to discuss here. There's a lot that they didn't discuss or that they're not alluding to as far as the geologic record. And so we'll dive into it. We're going to be discussing the late Ordovician extinction 445 million years ago and the late Devonian extinction 372 million years ago. That's the date they claim, but geologists put the late Devonian extinction at 375. Not only that, there were 3 extinction events in a row, and the earlier one in the Devonian is actually the major one, which they didn't discuss at all. So we will discuss that. We will get into their methodology, and I look really weird when I move around. My head gets all weirded out.
Yeah, the whole blurred background thing is strange.
All right, you got. If we do have time, we'll dive into another topic that we've been discussing at length: the whole theory of panspermia and how did life evolve here? Are we aliens? An article called "Primordial Surf" and a subsequent paper. They discuss the process of microlightning in mist, and it's pretty fascinating, and we'll dive into that if we've got time.
Mm-hmm.
Anything you want to talk about before we dive in?
Well, just as far as the extinctions go and dating them, I can really see from another related paper called Supernovae Dust Evolution Probed by Deep Sea Iron 60 Time History that was published in 2023, goes into some detail about how you would identify an iron 60 signal related to supernovas. And to me, this analysis makes it very clear how difficult it is to pin things down when you're talking about millions of years ago, like on that scale. Everything gets kind of fuzzy. Our ability to be super accurate kind of disappears sort of no matter what we do. So it's not really surprising that some of the very long ago extinctions are hard to pin down.
I would agree with that. Do you see the screen?
I do.
All right. So the concept here and what we're looking at here is a shot from maybe James Webb Space Telescope, maybe Hubble, showing a supernova explosion in the distance here.
Mm-hmm.
Now, before we dive into it, it's probably pretty important that we do some basic science to get started. And let's just talk about iron in general before we start talking about iron 60.
Mm-hmm. Iron
naturally occurs on rocky planets like Earth, but it occurs in stable isotopes. So about 6% of the iron on Earth is iron 54. The majority, over 91%, is iron 56. And then there are small amounts of iron 57 and trace amounts of iron 58. There's no naturally occurring iron 60. It's one of the known radioisotopes or 8 nuclear isomers, which are radioactive and they break down.
Mm-hmm.
The most stable of these radioactive isotopes is iron 60, and that's why we could find it. It's stable. So it's in the ground if it's deposited extraterrestrially. If you go look into iron 60, as early as 30 years ago, they claim that iron 60 is a remnant. It's left over from the Big Bang. The only way you can get these heavier isotopes, according to science, then was extreme high temperatures. Our sun doesn't even produce the temperatures necessary to make iron 60. You would need an exploding sun to create this, or a big bang.
Well, that also doesn't make sense simply for the sole reason that the half-life of iron 60 is only 2.6 million years.
Why doesn't that make sense?
Well, if it's from the Big Bang, then why would it still be? If it was only from the Big Bang, then why would it still be around?
So in the last 2 decades, there's been studies done on the half-life of iron 60. They haven't been able to pin down the half-life until recently, and they did come up with 2.6 million years as a half-life, which then we can use as a chronometer or a timing mechanism so let's say we take a core sample in the ocean, we find 8 meters down, there's a layer that has iron 60, we take out the iron 60, and the way that they're figuring this out is in that unit, they measure the ratio of iron 60 to, guess what, iron 56, or a stable isotope that it's breaking down to, and then they can calculate how long it's been sitting there. That makes sense. That's how they do half-life calculations. So what we now know in the last few decades is that iron 60 is being produced by exploding stars nearby. They have to be nearby. If they're any further than, let's say, 500 light years away, there's no chance that that explosion is going to make it here in any substantial way to have any substantial effect. So,
Darn, I even had a number for what that distance would be, but I don't know.
We'll get to that. I have it up here somewhere.
Okay, all right.
Because I think we have it in parsecs and light years.
Yeah.
21.67 parsecs is something I'm thinking about.
Okay. Well, by the way, for our listeners, a kiloparsec, so 1,000 parsecs, is equivalent to 3,260 light years.
All right, let's dive in. So here's the article from physics.org that came out on the 13th. That's just 2 days ago. This is how up to date we are on science here on the channel. We cover breaking news. Now, this might also be bad news for the micronova community because we don't find iron 60 being deposited every 12,600 years in a layer in the ocean.
Right.
So that's an issue. Right. But it does appear that every 3 million years or so, we get a deposition of this iron 60. And the iron 60 deposition lasts for up to 1 million years or more. So
yes, which is really interesting.
Right.
Yeah.
So what we don't know is anything. That's what I gleaned from reading this paper is they don't know anything. They don't know anything about supernovas. They don't know anything about supernova bubbles. They don't know anything about the supernova blast front. They don't know the thickness or the debris field. They're guessing about everything. Is that what you got from this?
Well, it depends on which paper you're talking about. The paper that this article refers to.
Yes.
For example, did you read both papers?
Yes.
Okay, yeah. So this particular paper doesn't actually, as far as I caught anyway, doesn't actually talk about the million-year deposition layer. It's the other paper that was actually looking at samples.
The supernova dust evolution probe in deep sea. Yeah.
And there's sort of several different models to explain how a nearby supernova would create these iron 60 layers, but we really don't know. We really are just guessing, but this is kind of how I feel about astrophysics in general. There's a lot of guessing and speculation, and there's a lot of speculation that's taken as kind of gospel, which is a problem. So
right, like stars are thermonuclear reactors that are eventually going to burn out, and that supernovas are the destruction of these stars. The problem with that is we've witnessed supernovas, and after the event, the star is sitting right there.
Right. Right.
All right. So I think that if we read this article, it's short. It really does a good job at concisely summing up everything we're talking about. So what's also interesting is the fact that this article talks about these extinctions specifically and no other ones, because in the Iron 60 paper that they're extrapolating this from, they're looking at an event just 3 million years old, not from the Ordovician or the Devonian.
Right. Well, and that's, I was going to mention that too. For the Ordovician or the Devonian, we're not going to be able to find Iron 60 evidence for a supernova causing those extinctions simply because the half-life of Iron 60 isn't long enough.
Indeed. So the article begins with this. At least 2 mass extinctions in Earth's history were likely caused by devastating effects of nearby supernova explosions. Researchers at Kiel University say these super powerful blasts caused by the death of a massive star, Assumption, may have previously stripped our planet's atmosphere of its ozone, sparked acid rain, and exposed life to harmful ultraviolet radiation from the sun. They believe a supernova explosion close to Earth could be to blame for both the late Devonian, unspecified, and Ordovician extinction events, which are speculative dating. The 445 date is not speculative. It's been confirmed over and over again. There's no real question about the Ordovician extinction at all. The big questions come in with the Devonian extinction event, which is actually a 3-phase event and very hard to explain, because all these, so in all these different events, the 3 Devonian mass extinctions and the Ordovician, geologists have explained them in all different manners: sea level drop, ice age, global heating, volcanics, meteorite, comet. All those have been used to explain these extinctions, but there's no real evidence. So that's the problem. What we do have is proxy data, and the proxy data, we can have an assumption on things like the O18 levels. So we can use other isotopes that have different half-lives or different ratios to come up with some conclusions on climate at this time. Now, as far as the extinctions go, the Ordovician extinction is huge. It killed 60% of marine invertebrates at the time. Now, during the Ordovician, if you were on Earth and standing on a continent, there wouldn't be any life. There were no plants. Grass hadn't even evolved yet. There was nothing. There's not even evidence of maybe a moss on the surface or a lichen. It would just be a rocky, I don't know what it would look like.
Yeah, it's weird to think about. It's hard to even imagine that.
Exactly. And so, but guess what happens after the Ordovician extinction event?
And then we get life on land.
Plants. All of a sudden, on the other side, there's plants. Where did they come from? We did have plant-like things in the ocean, but they certainly weren't like grass. The things that were living in the ocean were, we have them today, more like sea stars and anemones and corals and brachiopods and clams. But no like seagrass yet. The seagrass went from land to sea. Isn't that weird?
Yeah.
So first grass is terrestrial and it's in land and marshes, and then it migrates. I guess it becomes salt tolerant and then it moves into the ocean.
Right.
But that has more to do with oxygen showing up in high enough levels that things can respirate out into in the atmosphere.
Right, right.
So prior to that, all the nutrients and stuff they needed was in the ocean.
Right.
But after the Ordovician extinction, something happened where things could respirate up on the surface.
Right.
So
and
thank God that happened.
Always,
What'd you say?
The question, as always, is, you know, if we get to the panspermia stuff, is like, okay, well, where does the genetic material come from for the life on land all of a sudden, right? Is it all a mutation from what was in the ocean? Does it come from somewhere else? How does that happen, you know?
Exactly.
Which came first, the chicken or the egg, right? Like, where's this, you know, where is the seed for the grass on land?
Yeah, there has to be an initial
where did the seed come from?
Grow the grass. Where did it come from?
Right.
All right, so we've got the Ordovician extinction, and that causes life on the surface to flourish. And then after life is flourishing on the surface, We've got fishes now occupying fresh water. The bony fishes, the time of the fishes is the Devonian. And then a mass extinction occurs, and these weird jawless platy fish that we have all of a sudden become the normal fish that we all know of today.
What do you
They
mean by
were-
jawless?
The early Devonian fishes were not like a fish you see like a sunfish or a bass.
Yeah.
They had armored plating on the top surface,
Yeah.
which could be due to increased cosmic radiation. We didn't have a very robust magnetic field, maybe, which is why nothing's growing on the surface.
Mm-hmm.
But after the Devonian extinction, the bony fishes disappear. And all we have is the new fish with scales and gills like today. Completely different animal.
Jawless. What do you mean by jawless?
They're called
Doesn't
the
have a
jawless.
mouth?
A bony fish, modern fish have a bone that forms a bottom jaw. These
Yeah.
fish did not have it. They only had an upper plate.
Okay. All right.
So they didn't have a bottom jaw. They had something
Okay.
else,
Okay.
which is kind of interesting.
Mhm.
So the Devonian extinction, well, the Ordovician extinction is the second largest mass extinction we know of. The largest is the Permian mass extinction, where 90% of everything died. Everything.
Mhm.
But we're not going to talk about that one. We may get to it. But the Ordovician's the second biggest. The Devonian extinction is all the way on the bottom of the top 5, is the 5th largest. So they're two quite different extinctions, but they're really not. If we look at the geologic or the Phanerozoic climate change chart, here is the Ordovician Silurian extinction,
Mhm.
and the end Ordovician you can see is the coldest time on Earth.
Yeah.
And the Devonian mass extinction, another bottom.
Mhm.
So climatically, something very similar is occurring. And the Ordovician mass extinction was caused by this drop down, or was happening during this climate shift there. And the Devonian mass extinction was during this baby.
Mm-hmm.
So we've got major changes happening at this time, but no explanation. And on one side of the boundary, we've got a whole group of animals. And on the other side, a completely different group of animals. As if overnight, someone said, let's get rid of these million species. And I got 4 million new species here. And they just threw them on the earth.
Mm-hmm.
So
Some people would call that God.
Go ahead.
Some people would call that God.
Right. But based on the limited data we have, we now know that evolution occurs in spurts.
Yes.
Which is why in the 90s, Niles Eldredge and his colleagues came up with the term punctuated equilibria.
Mm-hmm.
Everything's fine for 100 million years. Something major happens to Earth, whether it be an expansion event where the Earth is growing, a major impact like Chicxulub, or in this case, a nearby supernova.
Right. Which could also be connected to the extremely cold period.
Yeah. In fact, these supernova could be triggering the cold periods.
Yes.
It says here in the article, past research has failed to identify a clear cause for either event, although they have both been linked to the depletion of Earth's ozone layer, which could have been triggered by a supernova.
Mm-hmm.
And we also know the ozone layer can be affected by magnetic excursions and reversals.
For the same reason, right?
Yes.
Because the idea behind this is a massive influx of cosmic rays, right? Which could happen with a field reversal or excursion, could also happen with a supernova. Those cosmic rays changing the chemistry, the atmospheric chemistry, and therefore depleting the ozone.
Yes, indeed. And here is more gobbledygook. Wait till you read this paragraph. Supernova occur when massive stars reach the end of their lives, run out of fuel, as if they get filled up at the Citgo.
Mm-hmm.
They cool off and then collapse under the pressure of gravity.
Mm-hmm.
There was just like 10 assumptions right there.
Mm-hmm. But this has been the model of what a supernova is for decades, right? So it's not really surprising to find this in an article.
The explosions are the biggest humans have ever seen. How many humans have seen a supernova explode?
Well, I mean, we've seen some with the naked eye even a few hundred years ago, but that doesn't mean that we understand what's happening.
Well, the most famous is about 1,040 or something, 50 around there, and a lot of petroglyphs are depicting the supernova at that time.
Mm-hmm.
So it says if a planet, including Earth, is located too close to a supernova type of event, it can have devastating effects. If a massive star were to explode as a supernova close to Earth, the results would be devastating. And this research suggests that this may have already happened.
Mm-hmm.
The researchers came to their conclusion after carrying out a census of massive stars within a kiloparsec, which you referred to earlier, 3,260 light years of the sun. That's pretty far, 3,260 light years.
Yeah, well, I want to mention too here, just for perspective, I find it really interesting that, as we just mentioned, there have been supernovas that humans have seen with the naked eye within the recent past. However, clearly those particular supernovas were not close enough to cause a mass extinction event. So just for some perspective about what you can see and how far away that might actually be.
Right. And in fact, 99.999% of all stars are farther away than a kiloparsec.
Right.
Right. I mean, the universe, if it's infinite, would be quite large.
Well, isn't that the understatement of the year? King of the obvious.
So the census allowed the researchers to calculate the rate at which supernova occur within the galaxy, our galaxy, the Milky Way, which is important for observations of supernova and the production of supernova remnants and massive stellar remnants such as, again, here we go, black holes and neutron stars through the universe.
Mm.
Okay, so what is the evidence? Well, let's first get to the late Ordovician mass extinction. It's often considered the second largest known mass extinction event behind the end Permian event. In terms of the percentage of genera that became extinct, the extinction was global, eliminating 49 to 60% of marine genera and 85% of marine species. Jesus.
Yeah.
So under most tabulations, the Permian-Triassic extinction exceeds this, but it is arguable. The late Ordovician extinction is massive. What also is going on in the late Ordovician, I've studied all these time periods. This is what I studied, Ordovician through Devonian, because there are amazing outcrops on the East Coast and the Appalachians of these time periods. So you can go out and look at them. During the Ordovician, something unique was happening on Earth. It's as if the Earth was being rattled. The deposits during the late Ordovician in most locations are turbidites exclusively, which are marine landslides, one after another in a sequence of 100,000 events continuing nonstop. So something during the Ordovician, picture the Earth ringing like a bell, or a continuous array of earthquakes occurring, which are causing these marine landslides to occur one after another. And this is exclusive to this period. So geologists can say whatever they think was going on there. But what many of them conclude is that the only deposits that were saved from this time period happen to be on the continental shelf where turbidites occur, which I don't believe that. There's only one environment that was saved on this entire time period.
Right, right.
It doesn't make sense. Also, from the Ordovician to the Devonian, there are no deep sea sediments. Everything is an inland sea. And we've referred to this during the whole Paleozoic. There's no deep ocean. There's no evidence of it. There's not one sliver of ocean from this time period that's the oceans we have today. All the oceans were on the current continents that we have today. So the entire center of the U.S. was an ocean. The only places above water were like the Appalachians and any other uplift in the West where there were volcanoes. The rest was covered by a shallow sea.
Right.
Still unexplained.
Right. So the problem with this, of course, right, is that the model of, you know, all of the land masses on Earth, all of the continental crust, all being stuck together with like the rest of the Earth being ocean doesn't make sense because we have no evidence of that ocean existing at that time. That evidence is non-existent. It's not there.
Right. And it would have been 70% of all the crust, but it doesn't exist anywhere.
Right.
So that's a hard one to wrap your head around.
Right.
So the late
Which,
Ordovician
you know,
mass
should
extinction
lead
occurs.
you to
Oh, go ahead.
sorry, which should lead you to expanding Earth theory, which we've done some shows about in the past, and I encourage you to go check those out.
Yeah, here's a nice little chart on the biota. And you can see these black lines, 1, 2, 3, those are the three, these are the two mass extinctions we're talking about. And in between the lines are completely unique groups of fauna that only exist in between the mass extinction lines. And then across the boundaries, everything changes and a whole new group of animals. And then it happens again, and then it happens again, and then it happens again. Now, the Permian extinction that killed almost everything on Earth, on the other side of that, we get dinosaurs. Where did they come from? Did a fish all of a sudden during a mass extinction get scaly, turn into a lizard, and jump on land?
Right.
It's hard to understand.
Our understanding of evolution is clearly in its infancy. There is a lot we don't understand, despite what an evolutionary biologist might tell you.
Oh, look, here's a picture of your jawless fish that you're confused
Yeah, I know.
See, he's got this big armored plate up for a head. Yeah. And the teeth were even built into the plate. So these are weird animals.
Yeah.
And so on the other side of that, you get regular fish like we have today, like a minnow.
Mm-hmm.
They lose the plating. They gain scales over a boundary. It's as if aliens showed up, reworked the genetics of everything that already existed to fit the new ecological niche.
Right. I mean,
that's a better explanation than anything we have.
Well, which you know, I can understand why people talk about ideas like the Anunnaki coming and creating humans because of these giant evolutionary leaps that we can't explain.
Well, and the Iron 60 paper discusses that the last Iron 60 event just happens to coincide when hominids walked upright.
Mm-hmm.
Right at that moment.
Mm-hmm.
2.5, 3 million years ago, we have this iron event, and then we get people.
Mm-hmm.
Before that, there were just apes.
Mm-hmm.
So the Anunnaki is represented by the black lines here.
By the way, the bony jawless fishes, did you say that the plates are only on the top of the fish?
Yeah.
That's interesting.
Well, we have some fish kind of like that. You know what a placo is that they put in fish tanks?
Yeah.
Like the sucker fish?
Yeah.
Yeah, they're kind of like, that's kind of what I think they would be looking like.
Well, the reason I find it really interesting is
the sucker doesn't have a jaw. It's just got that big sucky thing.
Right. But just having a bony plate on top in the ocean is interesting. On land, it makes more sense as let's say, a protection from predators, because they're not, a predator isn't necessarily going to be easily able to get to your underbelly. Yeah. But that is not true for a fish in the ocean, right? Like a predator can come from any direction, top, bottom, side, which would sort of suggest that the plating is, huh?
Trilobites were huge in the ocean. These are bottom dwellers. They were plated on top, soft underneath, like a pill bug. And so the fishes evolved the same way. They were just cruising on the bottom and only needed protection from the top.
Oh, they're bottom feeders. Okay.
It wasn't until after this line that the fish were now free swimmers all over.
Okay.
But they lost all of the plating.
Right.
So maybe this made them faster and more maneuverable, and that's how they survived.
Maybe. Well, the reason I brought it up was because it made me think that perhaps this is protection from something else, not predators, something that comes from above. like, I don't know, cosmic radiation or something like that. But you're underwater, which also provides protection. So,
Yeah, the water would be the best protection for radiation.
right.
In fact, they're thinking of using water in like space stations for that to protect from cosmic radiation.
No, that's interesting. Yeah, that makes sense.
But you need a lot of water.
Well, also you have a lot of complications from, let's say, using water in that way, right? Because water sloshes around, which creates big issues with inertia and momentum. So it's got to be tricky.
Yeah, but we do have that alien technology that no one knows about that Bob Lazar talked about. So gravity really shouldn't be an issue, or sloshing, once you can bend space and time. Wonder when they'll tell us about that. So let's talk about the late Devonian extinction, which is quite controversial. And let me see if I what?
I just remembered something that I was watching recently about very large like freight ships that actually use these intricate I don't know what you would call them, but the intricate sort of baffle system to modify this. So they use water in their hulls to make it so that they can navigate stormy seas without much risk of toppling. And so you're using the water to do that. And in order to control the weight, you have this sort of baffling system. So it just made me think of that for the reasons we were just talking about.
Cool. Back to the mass extinctions. We've got 542. Prior to 542 million years ago, everything was a algal mat. That's it. We got 2 billion years of algae. And then 542 million years ago, the Cambrian explosion. In a single day, thousands of species showed up. No explanation. Many of them don't even have a phylum. So these are creatures that don't fall into any of the current phylum of animals on Earth, which you would expect during the first explosion of life, it would be alien and we wouldn't know what the heck it was. And that's exactly what happened during the Cambrian explosion. Google the Burgess Shale. There were creatures with 12 sets of legs and 8 sets of eyes. It was as if God was just getting started and he was terrible at it. Yeah, hallucinogenia is the name of one of the creatures.
But also the fact that none of the phylums of those creatures match any of the phylums that we have today tells you something very important about evolution, which is that it's not linear as we're often led to believe. You know, the idea is that everything evolved from something that came before it. Rather, it's interrupted and interrupted.
Yeah, punctuated equilibria.
Right, actually, but even punctuated equilibrium still typically suggests that there's kind of a linear process, that it just happens that you make big leaps all of a sudden, but it's still a derivative of what came before it. This would suggest that that's not, and all of these extinction periods where we suddenly get all of these creatures on the other side suggest the same thing. That is not linear at all.
It's almost like God's playing a joke, because let's go to the KT boundary. He preserved dinosaurs across that mass extinction in the form of a chicken. It's almost a joke. So he erased all the giant, terrifying Tyrannosaurus rexes and all the things that were eating everybody. And on the other side, he left a chicken.
You know, I have
that would be de-evolution, in my opinion.
Well, maybe not. I mean, look how long the chickens have made it. But it reminds me very strongly of a quote that I really want to go run and get now about the idea that, you know, that the whole point of sort of life on Earth is God learning to express himself in every possible way, right? And like that all of these periods are different experiments in that. You know, it's every possible variation of what and the expression of God could be.
Exactly.
Yeah.
It certainly is the universe, though.
Yeah.
All right, so we've got the Ordovician Silurian mass extinction, which may be a supernova event here. Boom. And now we're talking about the Devonian extinction here, which is actually 3 parts. None of the 3 parts actually fall on the boundary. And Most of them are unpronounceable. The first is called the Gaveshan. I don't know. Would you have gotten that from there?
Gaveshan, what I would have said, yeah.
This is the N. Frosnian and the Flaminian. So you got the Gaveshan, the Frosnian, and the Flaminian. And these are all localities where extinction events were located. So the Gaveshan locality is in Gavesia or wherever that is.
So
most
all
of
of
these
these extinction
most of
events
these are in Europe, okay? Which is interesting because the same rocks on the other side of the Atlantic are also on our side in the Appalachians.
Mm-hmm.
That was the evidence of continental shift. When they matched up the same exact rocks on both sides of the Atlantic, they were like, wait a minute. Then they looked at a map and they said, oh my God, they fit together.
Right.
Yeah.
So question, the locations are refer to where we found the evidence, or is the implication that the extinctions only occurred in these places?
The extinctions were located at the localities, which are then corroborated at other localities worldwide, but they're still named the type locality.
Okay, so they're
Everything
not
in
limited
geology
to
goes
those.
back to the type locality.
Okay.
Yeah.
Okay.
So the Enfrosnian was found, you could probably read about it, in France. Well, it has the Frosnian Flaminian is also referred to as the Kellwasser event. So obviously that was the guy that found it in another place, right?
Mm-hmm.
These were not big extinction events. It says right here, 19% of all families and 50% of genera became extinct. So it's kind of a moderate extinction.
Mm-hmm.
There was another mass extinction in the Devonian called the Hongenberg event or the N Devonian extinction. And that's actually the boundary, which is not here.
Mm-hmm.
So this line is the one I just talked about, that black line. And these red lines are other extinction events. The biggest extinction event, the 50% killer, is the Frosnian. This one right here, which is not the one they refer to in the paper.
Just to make things a little bit more confusing.
Yeah, it's very confusing. So now there could be every 10 million years, there could be a supernova happening here.
It would still have to be pretty close.
Yeah.
But that's certainly possible, right? Like if we happen in this time frame, let's say between, 400 million years ago and 360 million years ago, if we were in that time frame passing close to a cluster of stars that has a high probability of supernova, that could explain it, right? Perhaps we passed through an area where a lot of supernovas could have been happening. I mean, that's certainly possible.
And it even alludes here in the wiki, although it is well established that there was a massive loss of biodiversity in the late Devonian, the time span of the event is uncertain, with estimates ranging from 500,000 to 25 million years, extending from the mid-Gaveshan to the N Flaminian. Some consider the extinction to be as many as 7 distinct events spread over 25 million years, with notable extinctions at the end of the Gaveshan, Frosnian, and Flaminian.
Interesting.
Because we've got Gaveshan, Frosnian, Flaminian, and then the one we just talked about, which is the end of the Devonian period, whatever it's called.
Mm-hmm.
The Hagenberg event. That ends the Devonian.
Interesting.
And then the Carboniferous period begins. This is when we get reptiles and amphibians and the precursor to dinosaurs. The Carboniferous period is amazing. Earth gets really warm, called hothouse Earth. We get 8-foot diameter dragonflies. We've got trees that grow up into near the stratosphere, maybe. I mean, we're talking 1,000-foot tall ferns. It was a weird time to be alive.
Near the stratosphere?
I mean, I'm exaggerating, but like the biggest trees we have today are the giant redwoods.
Yeah.
Those would be like saplings at this time.
Right. Well, what's that tree that's in Australia that's like a I don't know what period it's from, but it's some ancient, possibly dinosaur era tree. I can't remember what it's called. It's some kind of evergreen.
Hmm. Yeah, there were
It's
weird stuff.
extremely tall.
There's weird stuff going on back here.
Mhm.
And yeah, and there was no one burning CO2. Look at how much hotter it was.
Yeah.
Even during the end Devonian, it got really warm.
Mhm.
Now, folks, we're right here, the coldest time on planet Earth.
Hmm.
And the mainstream science is publishing papers saying that we're all going to die.
Mm-hmm.
It's absolutely insane. Okay, so what did we glean from this paper? That we don't know anything about anything going on. We've got these mass extinction events. They're probably driven cosmogenically. All things life is cosmogenic. We've talked about the idea of panspermia. We've talked about the, well, let's take it to the next level. The spraying of water microdroplets. They form luminescence caused by chemical reactions. And what they call it is microlightning.
Mm-hmm.
And this is between nanoparticle water droplets with different charges. So a static, it's like a static shock occurs between the droplets.
Mm-hmm. Mm-hmm.
And they've replicated this in the lab.
Mm-hmm.
And what we did have hundreds of millions of years ago on Earth was probably water spray from wind, from wave action, from waterfalls, from rain.
I want to point something out. You know, there's something very special about the chemistry of water. Like a water molecule is actually polarized. It's, you know, more positively charged and more negatively charged on either end. And because of that, that is the reason why when you freeze water, it actually expands when it becomes a solid. Most substances contract when they become solid, but water is different, and it's because of that. But that polarization obviously would also sort of make this, in part, make this micro lightning possible, simply because you have a voltage difference at one end of the molecule to the other.
Yeah. And the Earth was covered in water as life was emerging. So the idea is here that tiny lightning streaks in a fine spray can power chemical reactions that generate molecules for life.
Mm-hmm.
Now, these ideas were posited as early as the 1950s when areas around lightning strikes were studied and they found the precursors of organic molecules in the forms of proteins.
Mm-hmm.
And then they replicated it in a lab. And
Mm-hmm.
guess what happens after they did that? Everyone was like, oh, yeah, but you didn't create life. And so they they poo-pooed it and said, nah, it doesn't mean anything.
Well, I mean, this is the interesting thing about this, right? You know, of course, we're always searching for the origins of life. And in a way, the people that poo-pooed it are right in the sense that all this does is it creates the organic building blocks for life, but it doesn't actually create life, right? That's the part that we haven't figured out. And as I said to you yesterday, you know, to me, this makes it very clear that there is no life without the spiritual world. The spiritual world is what animates life. I don't know that we'll ever find a purely scientific answer for how life becomes animated, because I think it requires the spiritual world. That's just my opinion. But it's sort of funny. I mean, it's funny because we keep looking for this, which is why people poo-poo it, because it does not answer that part of the question. It only answers where the material comes from.
Exactly. And if we're in an infinite universe and things like the Akashic record mean something, everything that has ever existed has existed before and will exist again. There is nothing new under the sun. Everything that ever could be has been somewhere.
Well, I mean, the implication really is that everything exists all the time. The difference is that for us, we live in a world with time where there's a past and a future, and not all things seem to exist at the same time. But if you can imagine a dimension that does not have time, it becomes completely different, and everything exists all the time, infinitely, because as I look at it, because in my view, God always exists, right? All of that is God. So there you go.
Charles Darwin thought life started in a warm pond. Others point to comets that plowed through Earth like us. Some suspect a bolt from the blue, a lightning strike into the ocean. But we've replicated all these in the lab and have never created life. Moreover, we found life in the most inhospitable environments, like on the surface of spacecrafts re-entering Earth. We have life at hydrothermal vents that are not living on oxygen. So the assumption that water and oxygen makes life, I think that is extremely nearsighted because it's not true. We've got hydrothermal creatures down on these vents feeding on sulfur. And so it has even been posited that there could be silicon-based life on other planets.
You know, I gotta find it, but I read a really interesting little article months ago explaining that basically does a very good job of explaining at a basic chemistry level why carbon and oxygen and water really are the best candidates for life, but that doesn't mean that life is exclusive to those elements and materials. You know, we know it's still possible because we see it, like you said, the organisms that feed on sulfur, and the possibility that life could be silicon based because in the periodic table it's very similar to carbon, but it's still not the most ideal element for that purpose.
I think silicon may be more ideal than carbon in the sense that we used it in some of the first radios, quartz radios and watches. This silicon crystal is monoclinic and it is a tuner. That's why we can create a radio from a crystal. And so I think it would be more capable of tuning in to the life force, the animation force, than a human.
I'll have to find that article and we can talk about it on the show another time, because it was very compelling to me. I just don't remember the details right now, but I understand what you're saying. And I think that's also very compelling.
Yeah, because humans have a biofield. We're an electromagnetic bag of water. And so why couldn't you get the same thing with other elements that can create their own biofield? A quartz crystal has a biofield because it is tuned in to the vibrations of our universe.
Something else I want to mention about this microelectrics and the poo-pooing of the experiment where they say, oh, look, you didn't create life. I think it's interesting because this has long been a fascination, right? This is the Frankenstein story, basically, right? Like the Frankenstein story is you have all of the building blocks for life there. You have the body, and then you electrify it to bring it to life, right? That's the story of Frankenstein. So we keep hoping that that's the way we can do it, but apparently it doesn't work. So...
Well, if the universe is electric,
right,
then everything is electric.
Right.
Interesting to think about.
Yeah, I mean, perhaps there needs to be a coupling between electricity and some spiritual force in order for this to work, or something like that, you know?
Which is very scary. The times we're going into with robotics, AI, and what if they figure out how to do that? Yeah. We're entering a very dystopian time. It's going to
already have.
Yeah, it's going to rapidly shift like you've never seen it before. If you think the last 5 years were interesting, the next 5 years are going to go 10 times faster.
Yeah, I mean, you and I have lived very interesting lives in this respect because we literally grew up with the evolution of the personal home computer, right? You know, when we were very young, we had Commodore 64s, all of that. And now here we are, roughly 50 years later, and we're looking at the potential for AI to like take over the world. And that might happen very quickly.
Yeah, before you were born, I was playing Pong. You could play a computer game on a TV.
I know.
And that was before the first computer. Yeah.
Yeah. We're only
I think
6
that
years
came
apart.
out
I'm not that far behind you.
1974 or 5, Pong
Right.
came out.
Yeah.
Might have been earlier, but it was to the general public. You could get it. It didn't cost like $1 million either.
Right.
The first computers were ridiculously expensive though.
Mhm.
And they barely did anything. 64K.
Right.
That's like one letter in a text. That's 64K.
Well, the 64K was merely for the operating system. If you wanted to do anything else, you needed like a floppy drive. So if you had a video game, the big thing in our household was playing Load Runner on the Apple IIc. And so you had a floppy drive that the game was loaded on. You have to insert that into the drive first, and then you're off.
Guys, if you enjoy programs like this, support Revolution Radio, where information never sleeps and truth breaks the spell. We do have to abide by FAA rules and regulations, but we can say whatever we want.
Mhm.
And that is very rare. There's only one other platform that occurs, and that's Rumble, which is why we're going to replay this on Rumble. Because if we put it up on YouTube, there's about 100 things we said that'll demonetize it.
Well, and it'll be demonetized anyway because Magnetic Reversal News channel on YouTube was permanently demonetized. So therefore, find us on Rumble at Magnetic Reversal News, and this video will go up at 8 p.m. Mountain Time tonight.
Yeah, go get it.
Yeah.
All right. So we didn't discuss the worst mass extinction, which is the Permian mass extinction. But what's interesting, a new paper coming out found that even though like 80% of all animals above the ocean and in the ocean died, plants did just fine.
Mm-hmm.
And so that is a very strange question.
But wasn't this in one specific area in China?
Yeah.
I wonder how true this was for other areas on Earth. Did
Right.
all the plants make it? Did most of them make it? Was it just this particular area?
Well, it definitely proves that it was some external event that only affected a certain type of animals, right?
Mm-hmm. Mm-hmm.
The ones that were respirating all died.
Mm.
So maybe it was an anoxic event.
Perhaps.
Plants don't need oxygen. They need carbon dioxide. It's plant food.
Right.
And so if you were to light the earth on fire and burn off all the oxygen by burning all the forests or something like that, some event, and they refer to events like this in all of these extinctions, an anoxic event where the oxygen is gone.
Mm-hmm.
Where does it go?
Right.
That's the question. And you know how it comes back? The plants don't die.
Mm-hmm.
The plants make oxygen.
Right.
They eat carbon dioxide. So if all the oxygen is used up on Earth, the plants don't die. They keep making it. As long as there's CO2. Go ahead.
This brings up this brings home that this is likely some kind of external event that affected our atmospheric chemistry in such a way as to allow the escape of oxygen or the transformation of oxygen into something else in our atmosphere, into another compound. So yeah.
Yeah.
Because like you said, where does it go otherwise?
It all gets oxidized.
Yeah.
And we do have these periods back here in the Paleozoic where there are large accumulations of iron-rich beds, iron oxides. Mm-hmm. And these are the oxidation events where all the iron rusts, all the oxygen gets used up in this oxidation process, which would acidify the oceans, kill all the fish, all the life in the oceans, not the surface, not the plants. Mm-hmm. The plants just need carbon dioxide. They don't care if there's any oxygen. They're making oxygen. Mm-hmm. What a show.
I've come to the conclusion that cosmic radiation is the source of all life and death.
That's a boom.
Thank you for listening to Revolution Radio.